Hello everyone. The modern lore of dynamic programming, also called SESV. In this tutorial, we're gonna learn how to apply SESV to solve any dynamic programming problem in a systematic way. This tutorial is a part of the Data Structures and Algorithms class. First, let's take a step back and understand what kind of problems that can be solved by dynamic programming. To understand what kind of problems that can be solved by dynamic programming, there is no explanation that's better than Richard Bellman, the man who started this dynamic programming concept way back from 1954, which is almost 70 years ago. You can click on this link to read the original paper of Richard Bellman about the theory of dynamic programming. Today, we're gonna have a look at some important highlights of Bellman's DP. You can click on this link to see all of the highlights we're gonna talk about today. Now, from Bellman's word, the problems that can be solved by dynamic programming are various multi-stage decision processes. If a problem is a varied multi-stage decision process, then it can be solved with dynamic programming. To explain it a little bit more, in these problems, we are called upon to make decisions which will affect the state of the system, and these decisions are equivalent to the transformations of the state variables. And by that very general definition, examples of these problems are basically everywhere in modern life. For example, planning of industrial production lines, scheduling a patient at a medical clinic, determination of long-term investment programs for universities, determination of a replacement policy for machinery in factories, programming of training policies for skilled and unskilled labor, or choice of optimal purchasing and inventory policies for department stores and military establishments, and a lot more applications, as long as the application or the problem is a various multi-stage decision process. So, to summarize, problems can be solved with DP are usually finding the most optimal. It can be value, it can be the sequence of decisions, or anything really in a multi-stage decision process. Again, problem can be solved with DP. It's finding the most optimal in a multi-stage decision process. Examples of problems that can be solved with DP virtually can be found everywhere in life. DP problems are basically everywhere. Now let's take a step back and think. Just a simple algorithm that can be applied and make almost every single aspect of life much more optimized and better. After learning DP, it will not only highly possibly help you to get a job offer, but also help you to think smarter in your daily life. Like, should I buy this or that? Or should I choose chicken or fish for dinner? DP can help you to make the most optimal decision. Just take a few moments and let this thought sink in and appreciate the beauty of this algorithm. Next, before learning how to solve DP with SESV, let's quickly have a look at how DP problems is solved with Bellman's theory. In Bellman's paper, he defines something called policy. A policy is a sequence of decisions. In DP problem, you're gonna make a lot of decisions, and a sequence of those decisions is called a policy. For example, if I have a map here, and I have to go from start to end, if I decide to go right, and go down, that's a collection of 3 decisions, and right, down is a policy. I can have multiple policies. For example, instead of go right, I'm gonna go down. So I can go down, right. And the collection of down, right decisions is my policy number 2. I can have another policy, that is the blue line here. Policy 3 that contains the following decisions, right, down, right. And that's all the policies I can have for this particular DP problem. So to go from start to end, I can have 3 policies. That's the same with 3 different paths. Now, a policy is the most advantageous according to some pre-designed criterion will be called an optimal policy. And this optimal policy is what Bellman is going to try to find with his theory. So back to our example. In this problem, we're trying to collect the most gold, and the blue path is collecting 1, 5, 7, and 1. That's the total of 14 golds. And that's the most gold that we can collect. out of 3 paths. The red path, we only have 10 goals, and the blue path, we only have 11 goals. So the policy, which contains the decisions of write down right, is the most advantageous between those 3. And this policy of blue is called the optimal policy. And the way Bellman solved DB problem is, he will try to find this optimal policy. And how did he do that? For finding the optimal policy, Bellman will try to derive the functional equations from the original information to get a mathematical function for that optimal policy. Now remember, Richard Bellman was a mathematician, so this thought may have occurred very naturally to him to solve problems this way. And we will look at some examples. In Bellman's paper, we're gonna see a lot of mathematical modelings of the original problem, and then we're gonna try to find a function that represents the optimal policy. Now, if Bellman's approach sounds hard to you, it is because it's actually hard that with Bellman's theory, solving DB problem is equal to finding an optimal policy by deriving functional equations. That means for our problem here, we will need to represent the problem in math along with the problem conditions, like we can only go right or go down, and problem's requirement that we need to collect the most goal. And then with those mathematical information, with Bellman theory, to find the optimal policy, one will derive those functions to get some equations that's going to represent the optimal policy, which is our blue line here. And that is a lot of human brain work. Sometimes we can derive these equations, sometimes we cannot. That is why Bellman's called his work is a theory, because he doesn't guarantee that we can always find the equations of optimal policy. So for solving DP problem with Bellman's, there's a lot of human brain work and little computer work. Why? Because once we have that optimal policy equation, the computer can calculate it for us very quickly, just like C equal to A plus B. But don't worry, today we're not learning to solve DP problems with Bellman's theory. Next, fast forward for almost 70 years, from 1954 to the time of making this video in March 2023, we're gonna see how to solve DB problem with MIT and as well as the rest of the world. MIT is one of the most prestigious institute of technology in the world. And currently, this is how MIT is teaching the world to solve DP with 5 steps. Step 1, define some problems. Step 2, guess part of the solution. Step 3, relate subproblem solutions. Step 4, recurse and memorize or build DB table bottom up. Step 5, solve original problem. If you click on this link, you'll be able to access the way MIT is solving DP problem. And everywhere on the internet, you will see similar approach like this, of people teaching students how to solve DP problems. Why I always work with some people, I can find a majority of people, software engineers, students, are very confused to solve DP problems with these steps. And that is why we're learning SAM's DP today. Next is our main topic today, how to solve DP problems with the modern law of dynamic programming. It's also called SAM's DP. In summary, to solve DP problems with SAM's DP, we have 3 steps. First, we solve DP by hand drawing all scenarios. Then we're gonna use depth first search to redraw our tree. Second, we calculate the information of interest asked by the problem statement. Third, we're gonna catch distinct depth first search calls to improve the time complexity of the solution. And by solving DP problem with SAM's DP, the solution is guaranteed by the law if you follow the steps correctly. To elaborate SAM DBs a little bit more, what do we do really? What we do is we actually solve the problem by pen and paper first. How? We solve the problem by hand and paper by following all possible choices at each stage. That means we visit all possible scenarios, and visiting all scenarios is the key importance, because if we miss one, it's no longer guaranteed that the result is the most optimal. For applying this to this problem, is basically from start here, we're gonna try all possible paths to reach to end and choose the path that collects the most gold. Here we have 3 paths, and those 3 are all possible scenarios that we can travel. And we already know the blue path collects the most gold. After solving the problem with pen and paper, we then leverage the knowledge we have learned about depth first search in part 1 to quickly turn our on-paper solution into performant code. And we're gonna learn how to do it in a minute. If you are interested in the paper, The Modern Law of Dynamic Programming by me in 2033, you can use this link. And this link is Bellman's DP, the original paper, The Theory of Dynamic Programming. Now let's officially talk about the modern law of dynamic programming. If you can describe your system as follows. A system state is comprised of a limited number of parameters that describe the status of your system. For this example, the system state parameter is the current position, which is where we are, and that is the cell number. So if we are here, the state parameter is 0, 0. If we are here, the state parameter is 0, 1. Choices to change state. It's a limited, known number of choices to change the system state, and you have the same choices at any state. So if we are here at 0, 0, our choices to change state is either going down or going right. And when we change state by going right, our system state is going to change from 0, 0 to 0, 1. If we decide to choose to go down, our system state is going to change from 0, 0 to 1, 0. Final states are the states that achieve your desired information. That is the state when we are at the start cell, which is 1, 2, because that's the destination we desire to go to. So 1, 2 here is one of our final states. The final states can be the states where we cannot choose any choices to change system state anymore. For example, if we are here at 1, 0, we decide to go down, and that is out of the map. And as we are out of the map, we can no longer have any choices to change the system state anymore. That means we cannot move anymore. And that is also one of our final states. Can reach final states. After a finite number of choices to change the state, we can reach our final states. And that's easy to understand with this problem. As you can see, if we keep moving, eventually we're gonna go out of the map or reach the end state, which is the destination 1, 2 that we want. So in our problem here, we can reach final states. Finally, the system must be able to fit in a computer in terms of RAM and CPU, and the cores to run the system must also fit in a computer in terms of RAM and CPU. That means we have the computer RAM and CPU large enough to store the information of this map, and the RAM and CPU of the computer has to also be large enough to store the information when we try all the possible paths from start to end. Now if we have a system like this, then SESV guarantees that we're gonna have a systematic procedure to design and code our solution. We're guaranteed to have the best answer based on our requirement. For example, finding max, mean, or the best course of action. The time and space complexity of the solution are always equal. The time and space complexity will be in polynomials, which is one of on squared, on cubed, and so on. It's definitely not gonna be in exponentials. The time and space complexity equals to the number of distinct states created during the course of running the solution. That is the guarantees. How do we apply SESV to solve problems? The way to apply SESV is, we will solve the DP problems by running its course. Running its course. You may ask what's course? All of the courses, which is all of the possible scenarios that can possibly happen, and we're gonna do it with small input size. And the ideal size is the 3-level depth first search state tree. Why? Because it's small enough for us to write down. And after we have this, solving the problem by running its course, we then tell the computer how to run its course by translating the way of running its course by hand into code. And after that, the computer can handle much larger input sizes. And that's how we're gonna apply SESV to solve DP problems. In a nutshell, what do we do really? What we do is we give the computer a comprehensive way of listing out all possible scenarios. Again, we give the computer a comprehensive way to list all possible scenarios, and then we choose the most optimal one. That's how SAMSDP solves DP problem. Next, learn SAMSDP step 5. In this step, we're gonna learn how to solve the DP problem by hand with pen and paper. And this deficit state tree is the outcome of this step. Solve the DP problem by hand. We're gonna get to this tree in a minute. But before that, we will learn that the most difficult step in solving DP problem is actually this step, solving the problem by hand. Now, some DP problems are straightforward. For example, climbing stairs, but some are challenging. For example, edit distance, even solving by hand. It's simply because for problems like edit distance, the choices to change state are not very clear by the problem statement. Once you can turn the problem information into choices, it is very doable. And if you follow the steps correctly, you'll be able to solve it by hand. Because all you need to do is changing the system states until it reaches the end states. So how do we do it? We're gonna list all possible scenarios with all available choices. And changing state is a very natural thing because we already have the choices to create a new state. So to list all possible scenarios, we simply keep changing the states based on the choices that the problem gives us until we can no longer have options to change states or until we have reached our desired states. So that's not really solving, that is just simply changing the states until we can no longer change them. Now, remember, if you haven't solved the problem by hand, don't even think about writing a single line of code. Because remember, the machine just repeats what is told to do. So if you cannot solve it, how can you tell the machine to repeat it? And finally, this hand-solved problem state data, the deficit state tree data, is going to be used to test if later your code is correct. So in short, how to solve the DP problem with pen and paper by hand. The summary is running its course. And when we run its course, we're going to choose small input size. 3 levels of deficit state tree is ideal and absolutely not bigger than half of an A4 paper. Why do we choose small input size? Because it's small enough for us to write it down. If you choose big input size, you won't have enough time in the 30 minutes interview session to draw out your tree. Next, after choosing small input size, from the initial state, we're gonna make all possible choices to reach all possible final states. And once all possible scenarios are listed, we're gonna choose the best scenario that asked by the problem. And that's how we solve DP problem by pen and paper. Next, I'm going to show you how to solve this problem by applying step 5, solving DP problem by hand drawing all possible scenarios, also called by running its course. First, we're going to choose small input sizes. 3 level is ideal, and that's why we have very small map here. We have a 3x2 map, and this is going to give me very manageable state tree. Step 2, from initial state, we're going to make all possible choices and reach all possible final states. So again, our problem is we need to travel from start to end. That means we need to go from here to here. So our initial state is here. So to start our tree, we are at 0, 0. That's where we have one goal. This is our initial state. Now we're gonna make all possible choices from this state. To identify the choices, we look at the problem statement, and we can see that right here, it's telling that we can only go right or go down. So right or down is our choices as a specific state. So from here, our initial state, we have 2 choices. One is down, and one is right. So if we go down, we have 1, 0. We have 1, 0. with 2 goals. And if we go right from here, we have 0, 1 with 5 goals. Now we have 2 new states. And from these new states, we're gonna keep changing state by making all available choices until we reach final states. So at 1, 0, we can go down or we can go right again. So if we go down from here, we out of our map. And this is one final state. So we're gonna stop here at the final state. If we go right, we're gonna see 1, 1. And we have 1, 1. That's gonna have 7 goals. And from 1, 1, we're gonna keep changing state by making choices. Up, go down, and right. If we go down from here, we out of the map. And that's the final state. If we go right from here, we are at our desired destination, which is the end. And that is cell 1, 2, with the goal of 1. And then we hit the final state of the end cell. This is the desired final state that we want. Next, we're gonna keep changing state from this state to reach all possible final state. So from here, we can go down or right. If we go down from 0, 1, we're gonna hit 1, 1. And at 1, 1, we have 7 goals. If we go right from here, we're gonna hit 0, 2. And at 0, 2, we have 3 goals. Next, we're gonna keep making all possible choices from 1, 1 and 0, 2 to reach all possible final state. So when we're at 1, 1, like here, we can decide to go down or go right. Just exactly at what we did here. So we can go down or go right. And if we go down, it's out of the map. So that's an end state. If we go right, we hit the end, which is our desired destination. And that's gonna be 1, 2 with 1 goal. And here is our desired destination. Now we're gonna continue with 0, 2, which is where we are here. We're gonna make all possible choices to reach all possible final states. And from here, we can go down or we can go right. So if we go down from 0, 2, gonna give us 1, 2 with 1 goal. And going right from 0, 2 is out of the map. So it's also a final state. So now with going down from here, we have another way to go to our destination. Now all of the states that we see here and all of the depth first search that we have are all of the possible scenarios, and they are listed in front of us. We then gonna go back to the problem and look for the information the problem is asking for, which is collecting the most goal. This is a depth first search state tree. The first depth that's going from start to end is this one. And that is down, right, right, which is the green path that we have here. We can collect 1, 2, 7, and 1 goal. That's gonna give us 11 goal. The second path is the blue path we have here, which is going from 1 to 5 to 7 to 1, which is what we have here. And that is right, down, right. And it's gonna give us 1 plus 5 plus 7 plus 1. It's a total of 14 goals. The last path that we have is the red line here, which is this path, where we go right, then down. That is right, and down, with a total of 1, 5, 3, and 1 goal. So right, down, gonna give us 10 goals. And now at step 3, we're gonna choose the best scenario asked by the problem statement, which is collecting the most goal. And it's obvious to us, that's gonna be the blue path, where we go right down right, and we have 14 goals. And that is how to solve DP problem with pen and paper, by hand, by running all of its course. And that is how we get that deficit state tree solution, with the answer of most goal path, with the path of right down right, with 14 goals. Next, learn SAM's DP step 6. We're gonna redraw this deficit state tree with code. So after solving this problem by hand, the tree we have, the solution tree of all possible scenarios, as you might recognize, this is a deficit state tree. It's the same tree that we have learned from step 1 to step 4. We have learned how to relate the code with the state tree, and now we're gonna do the opposite. We're gonna use this state tree to create a code. Now let's translate this tree into code. First, we're gonna have the wrapper function. Second, always name your recursive function a deficit function to emphasize the role of deficits in DP. Next, at each state, we have 2 choices, and we know that the number of choices equal to the number of recursive calls. So 2 choices gonna give a 2 deficits call, and we can just simply write down like this. Next, state variable. To determine where we are at on this map, we need this number, the position of the cells. For example, 0 is 0, we are starting position, which is here. So our state variable is I and j. Next, changing state. When we go down, for example from 1 to 2, that is where we increase I to 1. So when going down, we're gonna be at I plus 1 and j. Next, the second choice to change state, where we go right, that's we're gonna increase j to 1. So to go right, we're gonna increase j to 1. And that is how we change the state. Next, final states. The first final states are going out of the map. So the conditions are, it's either I is out of the map or j is out of the map. And we simply return to stop the recursion here, and so on. Next, there's gonna be the state where we reach the destination, and that is where I and j equal to 1, 2. So I equal to 1 and j equal to 2. These are our final states, which are the base cases of our recursive deficit search function. Now to check if our recursive function gonna create the same tree that we want, we're gonna print out the nodes as ij to compare it with the state tree that we have. And we're gonna start as position 0, 0. Now if we run this is the nodes that we have. And we're gonna compare these nodes with the nodes that we have in our deficit state tree. So the first depth from this tree is 1, 2, 7, 1. 1, 2, 7, 1, which is what we have here. They're the same. The second depth is 5, 7, 1, and that is 5, 7, 1, and that is what we have here. So they're the same. The last depth is 3, 1, 3, 1, which is what we have here. So by this comparison of what we have on the console with the data that we have on the deficit state tree, we can be confident that our code is producing the same deficit state tree where we solve the problem by hand. And that is how we know the computer is repeating our solution correctly. Now remember, this recursion has an exponential complexity. That's where we have 2 choices, and the tree go m level deep. In this case, m is the number of columns of the map. And this is a bad time complexity, but we're gonna fix it in the next few steps. To recap, the time complexity is usually exponential. At step 6, using deficits for full branching, we have 2 choices. That's gonna be 2 to the power of n. 3 choices, it's gonna be 3 to the power of n. We don't have to worry about this part for now. And always remember, the number of choices at each state is equal to the number of the recursive deficits call. Now, to speed up translating the hand-solved tree to code, there are a few popular patterns that we can remember to quickly translate the tree into code. The first pattern is a few choices. In this pattern, from the problem statement, we know that we have only a few choices. For example, climbing stairs, we have 2 choices of making 1 step or 2 steps. And the tree is gonna look like this. And you know 2 choices equal to 2 deficits. So the code is gonna look like this. If we have a few more choices, we're gonna have a few more lines, a deficit. The second pattern is n choices. That means we're gonna have an array of choices given by the problem statement. For example, in this problem coin change, we have n choices with the n type of coin values. We have coin of 1, we have coin of 2, and we have coin of 3 values. This array of input can be more or less. It is not fixed like a few choices that we have here. We only have 2. This n choices can vary by the input of the problem. So with this type of problem, the deficit state tree is gonna look like this. At each state, we have n choices by the problem statement. For example, the red rectangle here or here. For this type of choices, the code pattern, instead of a few deficit recursive calls, we're gonna have to run a for loop to all of the choices and place the deficits call in there. You can imagine this type of writing the code is a shorthand of writing n of the choices like this. And this kind of for loop in the red rectangle here gonna create this kind of tree. The third popular pattern is full data point combination. And what that means is we are given a lot of data, like this array here, that have 4 data points. And the question for this particular problem usually asks for the full combination of 1 data point to the rest of the data points. So for example, if we're looking at data point 1, we need the combination of data point 1 with 0, 2, and 3, which is the rest of it. So if we have 1, we have 3 choices, which is the rest of the data point. And if we have 0, we have 2 and 3, which is the rest of the data point after 0, which is what we have here. And with that pattern, if we have 2, we need the combination with the rest of the data point, which is 3 that we have here. And it's gonna be the same for all the rest of the tree. So if we run this tree, if we print out the path of the deficits, we can see that we have the combination of 1, which is here, with 0, with 2, and with 3 in all possible ways. It's from this line to this line, all possible combination of 1. The next one is 0. We're gonna have all possible combination of 0 with 2 and 3, which is what we have from this line to this line. And the next one is 2. We have all possible combination of 2 with 3, which is 2 or 2 and 3. And the rest is 3, which is what we have here. So this kind of tree provides us with full data point combination. We can have any possible combination with a data point to the rest of the data points from the input. And to create this kind of tree is pretty simple. It's actually this one with just one small modification. That is, instead of the for loop starting from 0 at every time, it's gonna start at I plus 1. That means if we are here, the choices of 1 gonna start from I plus 1, which is 0, to the end of the array, which is 0, 2, and 3. We can check the correctness of the code with the deficit state tree that we have by printing out the state variable that we're interested in for each kind of pattern and compare it with the node. Now, one thing to remember, the time complexity of recursion as very high. For example, for a few choices, the time complexity equal to the number of choices to the power of the data length. For n choices, it's n to the power of n. This is very bad, but we don't worry about it for now. We have a way to make it much lower. And for full data point combination, time complexity of n to the power of n2. These three types of depth search, state tree generation code, is very popular. If you want to speed up the coding, where we translate the state tree into code, you should learn these patterns by heart. So you don't have to think about the code when you see the tree. And these are the few examples of DP problems in the type choices falling to our category. Next, learn SAM's DP step 7. Once we have the code, let's draw out the tree. We're gonna calculate the information asked by the problem statement. So for step 7, calculating the information, this step should be easy because we have learned about depth search. And this is a depth search tree with a depth search node visitation pattern. We can collect the data top down. That means we collect 1, and we collect 2, and we collect 7, and then we collect 1, and then we have the depth search path of 11. Or we can collect the data bottom up. That means we're gonna go all the way down and start collecting the information from the base cases. For example, if we go all the way down here, when we at the end state, we're having one goal, so returning one goal. And when we are at 1, 1, which is this cell here, we're gonna collect the goal of this cell, and from the two choices of down and right, we're gonna choose the bigger number to collect. So that is 7 plus the max of down or right. In this case, that's gonna be 1. So we're gonna have 8 here from bottom up. So in order to collect bottom up at the base case where it is the desired destination, we're gonna return the goal of the destination, which is 1 here. And at the base case where it's out of the map, like this one here or here, we're gonna return 0. As a general case, we're gonna return that node goal, which is where we are 7. We're gonna return 7 plus the bigger goal between the two choices of going down or going right. And that is between 0 and 1. And that is here, the max number between going down and going right. Now remember, for the dynamic programming solution purposes, always, and always do your calculation bottom up. Always. Because that's the only way you can catch for better performance in step 8. So if we run our step 7 calculation, our result is gonna be 14, which is the most goal path. Next, learn SAMDB step 8, catching distinct recursive depth search calls. Now after step 7, we already have a full working dynamic programming solution. What we're gonna do in step 8 is we're gonna make that dynamic programming solution more performant. Meaning we're gonna bring down the exponential time complexity to the polynomial time complexity by catching. So what do we catch? If you can see here at our deficit state tree, we have quite many repeating states. By looking at this pink oval, we can see that 1, 1 state, which is where we're gonna call deficit 1, 1, happens here. And it is repeated at a different place in our tree. That is where we are at this position. The first time we are at this position is this path, down, right, right. And we're crossing it one time. The second time we're at this position is this path, right, down, right. And by this in the physical world, what's happened in the code is, by looking at our tree, we see that this state happened 2 times, one here and one here. And that means our depth search 1, 1 is called 2 times, one here and one here. And because we are doing bottom up with the call to depth search 1, 1, we know for the first time it's gonna return 8. That is 7 plus max of 1 and 0. So what we do is we're gonna catch it. So we remember depth search 1, 1 equal to 8. The next time on this branch, where we go right down right. When we are at 1, 1, we don't have to run down the tree anymore. We can just look at the catch and we see a value, so we can just return 8. And by catching the return value of a depth search call, we're gonna dramatically improve the time complexity of this tree. So you can quickly see that if we catch all the distinct states, we're gonna have 6 of them. That is the total number of the positions that we can see on the map. Position 0, 0, 0, 1, 0, 2, and so on. And the distinct depth search call is in pink here, which is what we see here. So when we see a non-pink state, we know that we have visited this depth search before. So we look at the catch and we return the value instead of branching down. So for space complexity, that's gonna be equal to the number of the distinct depth search calls. And our depth search call is distinguished by I and j here. For this case here, I can go up to 2, which is the number of rows, and j can go up to 3, which is the number of columns. So the distinct depth search call in general is gonna be n multiplied with m, and that's gonna be the total number of positions of this map. For time complexity, we can see that in our entire tree, we only need to visit the pink nodes. If we are at a non-pink node, we can just look at the catch and return the value. We don't have to run it. So the time complexity is the number of times where we visit the pink nodes, and that is equal to the size of our catch. So remember, we always catch the distinct depth search call, and it's equal to the number of distinct states of the system. The catch space complexity equal to the total number of distinct states of the system. The catch key is the information to identify the current state, which is all the state param combined. And that is what we have here. So when we run a depth search, we're gonna create the key with I and j, and we check the catch. If it's not undefined, that means that we have visited the state before. We can just return the value of the catch. Otherwise, we run everything at normal, and once we have the result, we put it in the catch, and then we return the value. So our catch content is the returned value of the depth search call. And this is also why we need to calculate the result bottom up. Then if we run our code, the results stay the same. We still have most goal of 14, but now the time complexity is much better. It's all n multiplied with m, and it's in polynomial time. And with this catching step is done, we actually done solving the DP problem. Next, learn SAMDP step 9. There are some tips to debug a DB program. These are the things that you're usually gonna see when you write your DP code in SAMDB way. Now always compare your code output, which are the state parameters, with hand-solved tree data. This is the most important part. If you fail this part, your entire effort after this part is meaningless. The second tip is, if you're not sure what's going wrong, just play log everywhere at every step, so you know where is the first place the bug happens. That means you can place the log like this. To check whether your depth search is going through, or you missing some base cases. The next tip is, you can print the trace depth search call, for example like this one. Before calling your depth search, you can just log it out. And in the console, you can see the parameter that it's calling, so you can use it to compare it with your state tree. The last tip is, if you see undefined, not a number, infinity, minus infinity, or macro stack exceeded errors, it's most likely that you're missing base cases, or missing the branch killing conditions, or you have some undefined variable in the calculation equation. Spend some time with the step to solve DP and use these tips. You're gonna be a pro in solving DP problem in no time. Next, learn SAMDB step 10. We're gonna summarize what we have learned so far. At this point, you know everything you need to do to systematically identify a problem if it's a DP problem and solve it step by step. This requires understanding the nature of the code stack code execution, the role of depth search, which we have learned from step 1 to step 4, how to solve DP problem by hand, which we have learned in step 5, how to code the deficit state tree, which we have learned in step 6, how to calculate the information asked by the problem, which we have learned in step 7, and we also know where the first calculation is, which we have learned from step 1 to step 4, and we know what to catch and how to catch to improve the performance of the solution. It sounds like a lot of steps, but actually when you apply SESV, there's only a few simple steps, like what we have here. Step 0 is check. You need to check if the problem is a multi-state decision process, or if it's not. You need to check if you can convert it to a multi-state decision process and apply DB to solve it. After checking in step 0, step 1, we solve the problem with pen and paper. Use deficits to code the state tree. Step 2, we calculate the information asked, bottom up. Step 3, we catch distinct deficit calls to improve the time complexity. That's our 3 simple steps to solve a DP problem. For the next 7 tutorials, we're gonna see how we can apply this process to solve a lot of dynamic programming problems. That is all for today's tutorial. Thank you for watching, and I will see you in the next video.